Assalamualaikum warahmatullahi wabarakatuh and good day to you. So now we will continue our lecture 3 with the title Basic Principle of Hydraulic and Pneumatic Technology. So under this lecture we will cover about Reynolds number, Bernoulli principle, losses in hydraulic and pneumatic system, and pressure rating. Okay. So next, flow in closed conduit. So the equation involved in this flow is to calculate area of conduit equals to volume flow rate over average velocity of fluid. Okay. So next, Reynolds number. So what is Reynolds number? So this is the formula for Reynolds number, and the importance of this Reynolds number is Reynolds number is to predict the flow pattern in different fluid flow situation. Okay, so the formula for Reynolds number equals to velocity of fluid times inner diameter times density and divide by dynamic viscosity, or velocity of fluid times inner diameter and divide by kinematic viscosity. Okay, this is the continuity equation. So for a steady flow in a pipe, hose or tube line, the wake flow rate, or wake of fluid passing a given station per unit of time, okay, W dot, is the same for all location of pipe. Okay, wake flow rate 1 equal to wake flow rate 2. Okay, and if the fluid is liquid, okay, so y1 equal to y2, so we get area times velocity 1 equal to area 2 velocity 2. Okay, and this is the ratio of velocity 1 over velocity 2 equals to, okay, diameter 2 squared over diameter 1 squared. Okay, and this is Bernoulli equation. Okay, there are different elevation Z1 and Z2, and this is the formula for station 1 and station 2. The formula for potential, pressure and kinematic. Okay, and this is the equation. Okay, so elevation 1 plus pressure 1 over, okay, gamma plus V1 squared over 2G equals to elevation 2 plus pressure 2 over gamma plus velocity 2 squared over 2G. And this is the energy equation for Bernoulli modification by adding the losses in hydraulic system. So the same equation, just plus pump head, okay, losses of pump head, okay, losses of minus by losses of motor head and losses of friction. Okay, friction is considered as main cause of energy losses in hydraulic conductor. So to calculate the friction losses, we will use Ducky equation. Okay, by calculate the head loss due to friction in pipe for both laminar and turbulent flow, and this is the formula. Okay, and F is friction factor. Okay, friction factor for laminar flow is equal to 64 over Reynolds number. Okay, and friction factor for turbulent flow, okay, so this is the formula. Okay, this is formula for pipe relative roughness. So pipe inner surface roughness over pipe inside diameter, and this is for pipe inner surface roughness. Okay, so different type of pipe, so there are different roughness. Okay, now we will learn how to read a Moody diagram.
We've figured out that there's something called the frictional head loss in fluid flow in a pipe when there's internal friction because of the pipe, the construction of the pipe, and because what happens inside the molecular forces of the fluid flowing through the pipe. To calculate the frictional head loss, we found this equation right here, which included what we call the friction factor. And when the flow was laminar, we could calculate the friction factor by taking the number 64 and dividing it by the Reynolds number. Note that we can find the Reynolds number by taking the density of fluid, and this should be a small v for the velocity of the fluid, times the diameter of the pipe divided by the internal viscosity or the dynamic viscosity of the fluid. Now, this is good if we have laminar flow, but what if we have turbulent flow? Well, for that we need what we call the Moody diagram. The purpose of the Moody diagram is to find the friction factor, that very same constant right here, which is unitless, for turbulent flow instead of laminar flow. And it's a lot more complicated for turbulent flow because it depends not only on the Reynolds number, but it also depends on something we call the relative pipe roughness. And we can calculate the relative roughness of the pipe by taking epsilon divided by the diameter of the pipe. We'll explain in the next video what that really means. All we need to do in this video is try and understand how to obtain the friction factor if the fluid flow is turbulent instead of laminar. So on this diagram, on the left side we have the friction factor, on the right side we have the relative pipe roughness, on the bottom we have the Reynolds number. Notice that we start by calculating the Reynolds number, so that would be no different, but let's say that the Reynolds number is greater than 2000. Below 2000 we have laminar flow. Above 2000 we first have what we call the transition region, and then we have turbulent flow. Notice that not until the Reynolds number gets well above the 2000 range, we have what we call complete turbulence. Between 2000 and some value, we have what we call transition, and it depends upon the relative pipe roughness. If we have greater roughness, the turbulence happens quicker. If we have less roughness on the inside of the pipe, the complete turbulence happens at a much greater Reynolds number. So it's not as simple and straightforward as we thought before. It does depend on several things. But let's say, for example, we calculate the Reynolds number and we found it to be 10 to the fifth or 100,000. By then you realize 100,000, that has to be turbulent. Well, it again depends upon the relative roughness of the pipe. But under normal circumstances, the relative roughness of the pipe is high enough. So let's say the relative roughness is 0.03. So we come up here until we meet the line that represents 0.03. Then we come over here, and that represents a friction factor of about 0.05 to 0.06. Now these numbers, since I have them hand-drawn, are not exact, so don't take them as exact numbers, but they're approximate numbers. But it gives you the picture of how it's done using a real Moody diagram. Notice that if the relative roughness of the pipe is greater, then yes, we would expect a greater friction factor. If the relative roughness of the pipe is not as big, then we expect a smaller friction factor. And of course, a smaller friction factor gives you a smaller head loss. A greater friction factor gives you a greater head loss. And it all has to do with the Reynolds number and the relative pipe roughness. And on the Moody diagram, we're then able to find the corresponding friction factor necessary to...
Now this is the formula to calculate loss due to valve and fitting. And this is the condition of valve or fitting, either wide open, half open, okay, gate valve wide open, and this K is referring to this factor. Okay, this slide showing the pressure rating. Okay, so a fluid power conductor must strong enough to prevent bursting due to excessive hoop stress on the wall of the conductor. Okay, and this is the formula to calculate the tensile stress. Okay, so this is tensile stress, and this is the pipe thickness, and this is the fluid pressure, and this is the pipe internal diameter. Okay, so when the stress, okay, sigma acting in the conductor is equal to conductor material tensile strength, so the pipe will burst. So we have to consider this one. Okay, and this is SF is the safety factor, and if the pressure between 0 to 70 bars, so that we will use 8 as safety factor and 6 for the pressure between 70 to 170 bars, and we will use 4 safety factor if the pressure above 170 bars. Okay, and that's all for our lecture 3. Thank you.